In this chapter, we will be discussing about molecules and materials. Here are some subchapters that we will discuss, including the Lewis structure, intermolecular forces, solid crystal structures, semiconductors, and some properties of materials like the boiling point, vapor pressure, and surface tension. Let's start with the Lewis structure. In principle, if you write a symbol of a molecule, for instance H2O, at this point you should be able to recognize that this is a covalent compound. Unlike ionic compound, for instance the salt of sodium chloride, in H2O, what happens is sharing of electrons. We have discussed this in Chapter 2. You can revisit Chapter 2 materials to understand this better. So in H2O, there is a sharing of electrons between the atoms, while in NaCl, which is an ionic compound, there is a give and take of electrons. Let's take a look at the NaCl first. We know that NaCl is a salt and it is formed of a cation, which is Na+, and Cl- as an anion. So this is cation, this one is anion. In the cation, we have the sodium metal releasing one of its electron, and therefore it will become the cation of sodium or Na+, and normally this occurs at the gas phase. On the other hand, for Cl-, the opposite happens, so Cl will receive one electron and therefore becoming Cl-. So this is also in gas phase. We have also discussed the corresponding energy factors for these processes. For instance, releasing electron, that has to do with the ionization energy, while receiving electron has to do with the electron affinity. You can revisit Chapter 1 and perhaps some of the Chapter 2 as well to be able to understand this better. So revisit Chapter 1, where we have also discussed about this. Now, in the ionic compound formation, the sodium will release electron, and the released electron will be accepted by the Cl, so the Cl will become Cl-, and the Na will become Na+. However, for molecules like H2O, which is a covalent compound, this doesn't happen this way. Instead, the electron will be shared between the atoms, and the way that we draw the arrangement of covalent compounds, we call it the Lewis structure. So for instance, we have H2O. We have H, O, and H. How do we draw the Lewis structure of this so that we can see how the electrons are being shared among these three atoms? So one of the first things that you should do is to calculate what we call, sum the valence electrons. We have also discussed about valence electrons, meaning the outermost electrons at the outermost shells. So H has 1, oxygen has 6. The other, for instance, like helium, has 2, nitrogen has 5, carbon has 4, the halides, so the group 17, like F, Cl, and so on, they have 7. And from here, you can sum the valence electrons for H2O because we have 2H and 1 O. So the valence electron or VE will be 1 for the first H, 1 for the second H, and the other for oxygen. We will have 6. So in total, we should have 8 electrons. Now we have to distribute the electrons. Distribute the electrons throughout the structure. And how do we do this? The easiest way to do it, first up, is to draw 2 electrons between 2 atoms. So here, let's write it down this way. Now, if you see a line in a structure, in a covalent structure, one line represents a pair of electrons or 2 electrons. And in this case, after we distribute the electrons, we can tell that we are missing some. For instance, in this case, we should have 8 electrons to be distributed. In this case, we have only put 4. So 1, 2, 3, and 4. So we are missing 4 more. We have to put 4 more electrons somewhere in the structure. It is noteworthy that when we have atoms like hydrogen and the halides like F, Cl, and Br, normally they are what we call the atoms that are placed at the edge. And they can only form a single bond. So, by remembering this rule, we know that there is no way to put more electrons between these atoms because hydrogen, chloride, and also brom, they are normally atoms at the edge like this, so at the edge of the structure, and they only form a single bond, meaning that we can only put one line which represents 2 electrons. So the rest of the electrons, still we need to put 4 more because we have to distribute 8 electrons, and in this case we only have 4 electrons. The only way to complete the structure is to draw 2 more electrons only in the oxygen atom. And this would be correct as this is fitting to the valence electrons. So we can see from here, the valence electron of oxygen will be 1, 2, 3, 4, 5, and 6. So those are the electrons initially from the oxygen. The hydrogen will contribute to 1 over here. The other hydrogen will also contribute to 1 over here. And from here you can really see that these 2 electrons are used together by H and O, whereas 1 electron is from H and the other electron is from oxygen. And this is what we call the bonding pair. This is what we call the bonding pair. And this one is what we call the lone pair because these pair of electrons, they are not shared with anyone. Instead, it just belongs to the oxygen, which initially has the valence of 6. Now we have contributed and distributed all electrons at the correct places. If we work with a more complicated molecules, H2O is rather simple. If we are to work with more complicated molecules, we also have to remember what we call the magic numbers, which is the Lewis structure. Normally prefer what we call an octet rule. Although, as we go on, we will see a lot of exceptions for this particular rule, but at this case, we can still stick to it to begin our journey with drawing a lot of Lewis structures. The octet rule says that the most stable state of an atom should have 8 electrons, because 8 electrons is actually the valence of the noble gas. So valence of noble gas. And as we know, noble gases are one of the most stable elements in nature. Therefore, having 8 electrons making the other atoms also becoming more stable. And in this case, we can see for oxygen, indeed, it now has 8 electrons around it. So 1, 2, 3, 4, 5, 6, and 7, 8. And in this case, the structure of H2O follows the octet rule. We will see some more examples to practice on to be able to draw the Lewis structures.